welcome to another module. So, we are looking at an example of the LMMSE estimation of the channel coefficients HL across each subcarrier L in OFDM wireless system. Alright, so let us continue with this example. Let us consider the received symbols, received time domain samples to be given as the time domain output samples as y0 equals 1, y1 equals half, y2 equals half, y3 equals half. These are the received time domain output samples. Therefore, the corresponding frequency domain symbols across the various subcarriers are given by the FFT of these time domain samples. Alright, that is what we did. Therefore, the frequency domain symbols YL on subcarrier L, these are given as the FFT of the time domain symbols y0, y1 up to yn minus 1. Okay, therefore, we have YL equals summation k equal to 0 to n minus 1 yk e to the power of minus j 2 pi kl over n. In our particular example, we are considering n equal to 4 subcarriers, correct. All right. So, we have YL equals summation k equal to 0 to n minus 1, that is 3 yk e raised to minus j 2 pi kl by n, that is 4, which implies that YL is equal to summation k equal to 0 to 3 yk e raised to minus j 2 pi kl by 4, which is basically e raised to minus j pi by 2 kl. All right, this is the output symbol YL on the Lth subcarrier. All right, this is the output symbol YL on the Lth subcarrier. All right, so now let us compute the various output symbols on the various subcarriers. All right, so we have Y0. Okay, so we can have Y0 equals summation k equals 0 to 3 yk e raised to minus j pi by 2 k times L equal to 0. So, e to the power of minus j minus e to the power of 0 is 1. So, this is simply summation k equal to 0 to 3 yk, which is simply y0 plus y1 plus y2 plus y3, which is equal to, well, 1 plus half plus half plus 1 equals 3. So, we have capital Y0, the received symbol on subcarrier 0, this is equal to 3. Okay. Now, similarly Y1 equals summation k equal to 0 to 3 yk e to the power of minus j by 2 pi k into L equals 1. So, this is simply e to the power of minus j pi by 2 k, which is equal to y0 plus y1 e to the power of minus j pi by 2 plus y2 e to the power of minus j pi plus y3 e to the power of minus j 3 pi by 2, which is equal to y0, that is 1, plus y1 half into e to the power of minus j by 2 minus j plus half into minus 1 plus y3, that is 1 into j e to the power of minus j 3 pi by 2 is j. So, this is half plus half j, this is equal to y1, okay, capital Y1, all right. And just to be clear, symbol on subcarrier or output, rather output symbol received on subcarrier 1, that is y1 equals half plus the output symbol received on subcarrier 1, that is y1, capital Y1 is half plus half j. Okay. Now, y2, that is given as summation k equal to 0 to 3 yk e to the power of minus j pi by 2 k into 2, which is summation k equal to 0 to 3 yk e to the power of minus j pi k, which is equal to y0 plus y1 e to the power of minus j pi plus y2 e to the power of minus j 2 pi plus y3 e to the power of minus j 3 pi, and this is equal to 1 plus half into minus 1 plus half into e to the power of minus j 2 pi, which is 1 plus 1 into minus 1, and you can see this is 0, therefore, y2 is equal to 0, that is output symbol on subcarrier 2, this is equal to 0. And now, let us compute y3, that is output symbol on subcarrier 3, which is summation k equal to 0 to 3 yk e to the power of minus j pi by 2 k into 3, which is y0 plus y1 e to the power of minus j 3 pi by 2 plus y2 e to the power of minus j, right, e to the power of minus j 3 pi plus y3 e to the power of minus j 9 pi by 2. Okay. This is what we have, and this is equal to 1 plus, okay, half into j plus half into e to the power of minus j 3 pi, right, correct, that is minus 1 plus 1 into e to the power of minus j 9 pi by 2, that is minus j. So, this will be half minus half j, that is y3. Okay. So, these are the received symbol across subcarrier 3, and therefore, now to summarize, the frequency domain outputs that is received across various subcarriers are capital Y 0 equals 3, capital Y 1 equals, well, half plus half plus half j, capital Y 2 equals 0, capital Y 3 equals half minus half j. These are the frequency domain outputs across the various these are the frequency domain outputs across the various subcarriers. That is, we have n equal to 4 subcarriers 0, 1, 2, 3, capital Y 0, capital Y 1, capital Y 2, capital Y 3 are the outputs, output symbols in the output symbols across these various subcarriers, that is n equal to 4 subcarriers, alright. And now we can compute the LMMSE estimate of the channel coefficient. Remember, the LMMSE estimate of the channel coefficient, that is given as, well, we have h hat, that is what we derived in one of the previous modules, h hat L equals L sigma h square x conjugate L divided by L sigma x h square magnitude x L square plus n sigma square into y L. Okay. This is the LMMSE estimate of channel coefficient LMMSE estimate of channel coefficient HL. Okay. And therefore, now remember we already know that we have the symbols loaded on the various subcarriers. These are given as x 0 equals 1 plus j, x 1 equals 1 minus j, x 2 equals, well, 1 plus 2 j, and x 3 equals 2 minus j. These are the symbols loaded on the subcarriers. Therefore, we have h hat 0 equals, now further we will need the prior variance. Remember, we will need also the prior variance sigma h square, the number of channel taps, and the noise variance sigma square, alright. Okay. So, let us assume L equal to 2 channel taps, h 0 comma h 1 with sigma h square equals, well, sigma h square equals, that is dB variance sigma h square equals 0 dB, which implies 10 log 10 sigma h square equal to 0, which implies sigma h square equals 10 pos 0 equals 1. Therefore, L sigma h square, since we have L equal to 2 channel taps, 2 into 1, that is equal to 2. Similarly, assume the noise samples time domain, similarly assume noise variance or rather dB noise variance sigma square equals, well, minus 3 dB implies 10 log to the base 10 sigma square equals minus 3, implies sigma square equals half, 3 dB is 2 minus 3 dB is half, implies n sigma square, where n is the number of subcarriers, remember, is 4 times half, that is 2. Okay. Now, we can derive h hat of 0, estimate of channel coefficient across tab 0, this is L sigma h square x conjugate 0 divided by L sigma h square magnitude x 0 square plus n sigma square into y of 0. This can be divided as L sigma h square is 2 times x conjugate, that is 1 plus j conjugate divided by L sigma h square 2 times magnitude of x 0 square, that is 1 plus j magnitude whole square plus 2 into y 0, which is basically we have derived y 0 above, that is 3. So, this is twice 1 minus j divided by twice into 1 plus j magnitude square, that is twice into 1 plus j magnitude square is 2. So, 4 plus 2 into 3, and now we can see there is a 6, there is, this is basically you have 3 into 2 6 in the numerator, 6 in the denominator. So, this is basically simply your 1 minus j, h hat of 0 equals 1 minus j. This is the LMMSE estimate of channel tap h hat of 0. H hat of 0 is the LMMSE estimate of the channel tap h 0 or the channel coefficient h 0 across subcarrier 0. Okay. Similarly, we can derive the estimates, LMMSE estimates for the rest of the subcarriers. All right. So, let us quickly derive them. We have h hat of 1, this is equal to, well, twice x 1 conjugate 1 minus j conjugate divided by twice magnitude x 1 square plus n sigma square, that is 2 times y of 1, that is basically your half plus half j. So, this is twice 1 plus j divided by 2 into 2 4 plus 2 6 into half into 1 plus j. Okay. So, this is going to be 1 by 6 into 1 plus j square, 1 plus j square is basically 2 j, that is basically gives 1 by 3 j, and this is your h hat, this is equal to your h hat 1, estimate of channel coefficient across subcarrier 1. Let us quickly do for h hat 2 and h hat 3. So, h hat 2 equals, well, that is equal to twice 1 plus 2 j, that is x 2 conjugate divided by twice L sigma h square 1 plus 2 j magnitude square plus n sigma square. What is n sigma square? That is twice into y of 2, but y of 2 is 0. So, therefore, this is no one. So, this is simply 0, you do not need to compute this elaborately, and the remaining one is h hat of 3. H hat of 3 is L sigma h square 2 times 2 minus j, that is x 3 conjugate divided by twice magnitude 2 minus j whole square plus 2 into y of 3, that is half minus half j, that is 2 divided by, well, magnitude 2 minus j square is 5. So, 2 into 5 10 plus 2, that is 12 times 2 plus j into half into 1 minus j, this is equal to 1 over 12 times 2 times 2 plus 1, that is 3 minus j plus j minus 2j minus j. So, this is 3 minus j divided by 12. This is the estimate h hat of 3. This is the estimate h hat of 3. So, the estimate h hat of 3 across subcarrier 3 is 3 minus j divided by 12. Thereby, we can compute the LMMSE estimates of the various of the channel coefficients across the various subcarriers. We can also compute the corresponding mean square errors of the LMMSE estimate, and we also derived the expression to compute the mean square error of the LMMSE estimate. Remember, the MSE of the LMMSE estimate on subcarrier L the MSE of the LMMSE estimate MSE of LMMSE estimate on subcarrier L, that is equal to 1 over 1 over n sigma square divided by magnitude XL square plus 1 over L sigma h square. So, let us compute this MSE for subcarrier L equal to 1, that is, what is that? That definition of that is h hat 1, I am sorry, for L equal to 0, we have to start with subcarrier 0, h hat 0 minus h 0 magnitude square, that is equal to 1 divided by n sigma square. Well, we know what is n sigma square, that is 2. Well, 1 divided by 1 divided by 2 divided by magnitude x 0 square. Magnitude x 0 square is magnitude of, well, that is magnitude of 1 plus j whole square plus 1 divided by L h square, that is 2. So, this is 1, 2 divided by magnitude 1 plus j square is 2. So, this is 2 divided 2, that is 1 plus half. So, that is 3 by 2, this is equal to 2 by 3. Okay. So, this is what is this expected value of magnitude h hat 1 minus h 1 whole square. Okay. The MSE associated with the LMMSE estimate corresponding to subcarrier 1. Similarly, expected value of magnitude h hat 2 minus h 2 whole square, this is given as 1 divided by 1, 2 divided by magnitude x 1 square plus 1 divided by 2. This is again 1 divided by 1 plus half, which is equal to 2 by 3. Now, expected value of magnitude h hat 2 minus h 2 whole square. Now, this is equal to, well, this is equal to 1 divided by 1 divided by 2 divided by magnitude, well, x 1 square. Magnitude x 1 square is magnitude 1 plus 2 j square, that is 5 plus half, that is 1 divided by basically 5 by 2 plus half, which is 1 divided by 3. Okay. So, this is this MSE is this mean squared error, and finally, expected value of h hat 3, again we can find that equals 1 divided by 1 divided by 2 divided by magnitude x3 square plus half. Again you can check, this will again be 1 by 3. Okay. So, basically what this example tells us, what we have done in this example is we have done an elaborate example. We have considered the transmission of the symbols loaded onto n equal to, we have considered the n equal to 4 subcarrier OFDM system with L equal to 2 channel taps, considered the symbols loaded onto the subcarriers, derived what are the samples that are transmitted in the time domain, considered the output samples received in the time domain, derived what are the corresponding symbols, output symbols across the various subcarriers in the frequency domain, alright. From that, using the properties of the prior variance of the channel of the channel taps and the noise variance, we have computed the LMMSE estimates of the channel coefficients, the capital H's across the various subcarriers. We have also derived the expressions for the mean square error in the LMMSE estimate of each channel coefficient, alright. So, that completes this comprehensive example on the MMSE estimation of MMSE estimation for an OFDM, orthogonal frequency division multiplexing wireless communication system. Thank you.